All right, so I think we actually know most of the stuff in this little section here, 2.3e. K, of course, is a constant, and we're just going to look at it. Is there anything that can change the KEQ? If it is constant, is there anything that can change the KEQ? Do you guys know the answer? Temperature, and that is it, okay? So if we change pressure, we will get a shift, but only if gases are present and only if there's different numbers of gas molecules on each side. If we change the, why did I do that one first? If we change the concentration of a product or reactant, we will get a change or a shift. If we change the temperature, we get a shift. If we add a catalyst, there's no shift. If we add an inert gas, there is no shift. Hopefully that is all review. Vera, I have your quiz here. Now, when we had a change in concentration, it shifts to get back to the original KEQ. So there is no change in KEQ. Okay? Same thing for if you change the pressure, as long as there's no temperature change involved, it shifts to get back to original KEQ. And if there are the same number of gas molecules on each side of the equation, the concentrations of products and reactants will have changed by exactly the same amount, by the same factor, and so the ratio between them will remain the same, so it won't have to shift. Temperature, on the other hand, shifts, and we get a new KEQ. So we have no change, we have no change. Okay, so only temperature can change the value of KEQ. How does temperature affect KEQ? It just depends on which direction it shifts. So if you can predict the direction of shift, you can predict whether temperature will increase the KEQ or decrease the KEQ. So if we have an exothermic forward reaction, so this is our type of reaction in the forward direction. If the forward reaction is exothermic, and we increase the temperature, then the system will shift to the left. And if the system shifts to the left, we end up with more reactants and less products, which means that KEQ gets if we have more reactants and less product, KEQ gets smaller. Did that make sense? Nobody's nodding. Ah, okay, good. Good. If it's exothermic and we decrease the temperature, it's going to shift to the right to release energy to bring the temperature back up. That's going to favor the product, so we're going to have more products, less reactants, and therefore KEQ will increase. It will get bigger. I don't know why I have this whole table for this. I think once you've figured out one of them, all of them kind of just follow from there. But shall we go through the last two rows anyway? Yeah, okay. So if the forward direction is endothermic, in other words, we've got our heat term here, and we increase the temperature, that's going to cause a shift to the right. That means we will have more product, less reactant, which means KEQ is going to get bigger. And if it is if the forward reaction is endothermic and we decrease the temperature, it is going to shift to the left, which means we have more reactant, less product, and so KEQ will get smaller. That's not something you have to memorize. You can just be like, okay, which way does it shift? Do I get more product? If I do, KEQ gets bigger. If I get less product, KEQ gets smaller. Yes? Yeah, no. What is KEQ again? Okay. God bless you. You know what? If you have that question, so does at least one other person in this class, and they were just too shy to ask. So good for you. Okay, so KEQ is the equilibrium constant, and it is equal to the concentration of the products divided by the concentration of the reactants. So it is the ratio of products to reactants. Now, if we want to get a little bit more specific, if we have a reaction A plus B in equilibrium with C plus D, then KEQ will be the concentration of C raised to the power C, concentration of D raised to the power D over concentration of A raised to the power A, and whoops, that looks like a D, A, and concentration of B raised to the power B. Yes? And we know that if KEQ is greater than 1, what is true? Products are favored. Tell your partner what it means that products are favored.
It's like later, like I think after 40 minutes of class, she's like gone. Like she put the bell. She have to.
It's all good. Don't worry. Don't worry at all. Alrighty, friends. What does it mean if products are favored? At equilibrium, there are more. There are more what? Products than reactants. We could also say the position of the equilibrium lies to the right. And today we're going to look at why that is. Why do some equilibria lie to the right? Why do some of them lie to the left? Why are some of them going to completion? Why are some of them not going at all? Okay. Let us do the contrasting one. If KEQ is less than 1, what can we say? We can say that reactants are favored. And what does it mean when we say reactants are favored? Yes, at equilibrium, there are more reactants than products. In other words, the position of the equilibrium lies to the left. Okay, so here we're going to take a little look at why changing to concentration does not affect KEQ. Okay, so here is an equilibrium. We have PCl5 in equilibrium with PCl3 and Cl2. Our KEQ expression, we've got our products over our reactants there. And let's look at our original equilibrium. And we're going to stress this equilibrium or disturb it by changing the concentration of PCl5. So we have added extra product. Now, that means that if we add extra product, or sorry, not product, reactant, we have added PCl5. So which direction will this shift? To the right, which means we are going to be using up PCl5, right? So it goes down, and we're going to be making PCl3, so it goes up, and we're going to be making Cl2, so it goes up. So if we look at PCl5 compared to where it was before, the new concentration of PCl5 is higher. What about the new concentration of PCl3? Compared to our original equilibrium, is it higher or lower? Higher. I'm going to get rid of all my drawing because it's just making it messy. Okay? And the new concentration of Cl is higher. So guess what? At our new equilibrium, KEQ is equal to bigger numbers over bigger numbers. And if both are bigger, if the top and the bottom are both bigger, then the number stays the same. Why does changing pressure not affect KEQ? Are we locked? Oh, dang.
And these are my things.
Okay. Why does changing pressure not affect KEQ? Well, if we look at changing the pressure, if we decrease the volume, what happens to all of the pressures? Or all of the concentrations? Everybody should be telling me this right away. So, since you're not telling me right away, I'm going to have you imagine a container that is the size of this whiteboard. Yes? And it has 1, 2, 3, 4 particles in it. Yes? And now I'm going to squish that. I'm going to decrease the volume. So this is now my container with the 4 particles in it. In which is the concentration higher? In this one. This has a low concentration. This has a high concentration. So anytime you squish a container, all the concentrations get higher. And you can see that because on all of these we have a spike. Yes, all of them go up. All of them go up. And then because we have squished the container, which direction are we going to shift? We are going to shift towards the side with more gas molecules or fewer gas molecules. Tell your partner. Good thing I didn't ask you that on the quiz. Holy mackerel. So if an increase in pressure was the stress, the equilibrium will shift to do what? To decrease the pressure, yes. Okay, we increase the pressure. The system is going to shift to decrease the pressure. How is it going to do that? Would it want to make more gas molecules to have that happen, or should it make more molecules into fewer molecules? Do we want to go from fewer to more or more to fewer? More to fewer. Okay, so we want to shift to the side with fewer gas molecules. Excellent. So which way will this equilibrium shift upon a decrease in volume? It's going to shift to the right. All right, but let's look at what happened to all of the concentrations. They all ended up being bigger. Yes? Bigger. And bigger. And since the numerator got bigger and the denominator got bigger, what happened to the ratio? Stayed the same. I mean, this is a long way of going around saying that temperature is the only thing that changes KEQ. But hopefully it's also reviewing some good concepts for you. Okay? And what's the ratio? The ratio is the KEQ value. All right. So why does changing temperature change the value of KEQ? Well, if you remember with temperature, what is a feature of a concentration graph that is missing when our stress is temperature? Vertical spikes. So what that means is that you can't have reactants and products all ending up bigger than they were before or smaller than they were before because you're shifting in one direction. So either products are going to get bigger and reactants are going to get smaller, or reactants are going to get bigger and products are going to get smaller. So in this particular case, the mixture is cooled. If we cool this mixture, which direction will it shift? It will shift to the right. Okay, which means we're going to make products. We have more product. And we have less reactant than before. And what that means is that this has gotten bigger at the new equilibrium. And this has gotten smaller. Therefore, the ratio gets bigger. Is good? Okay. Do you guys want to try this one? Example number 1. Is anyone unhappy with this question? Yes. Not just because they're not gases, but they're also not. We have a solid and a solid and one single liquid. So that was a trick question. I don't know if I meant it to be a trick question. You can look at the answer key and see if I answered it the wrong way. But anyway, if there had been a KEQ for this, it would have gotten smaller as the temperature increased, and it would have gotten greater as the temperature decreased. Okay, if there had been a KEQ, but there is no KEQ. All right, why don't you try example number 2? And we've not given you any states here, so let's assume they have concentrations. For number 2, did you get increase, decrease? Thank you all for answering. I appreciate it. It's awesome. It's fantastic. Feel free to carry on to number 3. Number 3 is asking the question in a different way. I don't know if we need to do example 4. If we've done example 3, it would just be the opposite, right? How do you guys feel about number 3? If KEQ increases, it must have shifted to the right. And if it shifted to the right, that means our heat term must have been in the reactants. Because if we increase temperature, it will shift to the right to absorb heat to bring the temperature back down. Okay, so I'm going to skip number 4 because it's basically the same. Feel free to do it and look it up in the answer key. What does the value of KEQ tell us? A large KEQ value tells us that the concentration of products is large. And the concentration of reactants is small. A small KEQ value. And what do we mean by large? Large means KEQ is greater than 1. What do we mean by small? KEQ is less than 1. And we've talked about this before, yeah? So this is nothing new. Yeah, I think we've talked about all of this just recently, so I don't think we need to go over that again. The larger the KEQ, the more the products are favored. The smaller the KEQ, the more the reactants are favored. You can actually get some KEQ values where, like, let's say we had, there's a thing called a KSP, which is a KEQ for a solubility equilibrium. And the KSP for Ag2S two Ag plus S 2 minus aqueous. This is like something times 10 to the negative, like a billion. Not a billion actually, but like a lot. 30? Okay, they can get really tiny. Okay, I'm totally making up that number, but it can be very, very small. Now, if the KEQ is classified as being very large, okay, we're going to put that in quotes, very large, that means that the concentration of the product is much greater than the concentration of the reactants. And essentially this reaction goes to completion. Do you remember that language from the summertime?
Oh, no.
Yes? So if a reaction goes to completion, it means all or most pen just died. Let's fix that. And the other pen. All or most of the reactants are used up. So basically, you end up with all product and no reactant. So let's look at an example of this in our data book, the pink one. So if you don't mind grabbing your pink data book, and you're going to turn to page, I think it's page 4. What page is it? No, it's page 6. Page 6. Sorry, not page 4, page 6. Now, do you remember your strong acids? What's the difference between a strong acid and a weak acid? A strong acid completely dissociates. That means that dissociation process is complete. It goes to completion. And you can see here we have our strong acids are at the top of the table. Okay, these are our strong acids in the gray. And they are given a K value. In this case, it is the KEQ for an acid, so we call it a Ka. Okay, that is just KEQ for an acid. It's called Ka. And all of these guys, they have one-way arrows. One way, one way, one way, one way, one way, one way. And their KEQ is very large, which means this goes to completion. All right, so you end up with all dissociated and then none of it undissociated. Okay? Yes. Yeah? Anyone else need one? There you go. Now, after we get past those 7 acids, you'll notice that we now have KAs. We have a Ka of 1 for water, and then everything else has a negative power of 10, and so those are all less than 1, which means and if Ka is less than 1, what does that mean about products versus reactants? That means that the reactants are favored. So, if Ka is less than 1 and the reactants are favored, do you remember when we wrote the net ionic equations, including weak acids? We left the weak acids together because mostly they are together because the reactants are together. Okay, so this is just looking at it from a mathematical perspective now. Okay? Okay, so that's why we keep the weak acids together in net ionic equations. I go back. Okie dokie. Now, if KQ is very small, the concentration of the reactants is much greater. So if we have KEQ is very small, concentration of reactants is much, much greater than the concentration of products. In other words, the reaction basically does not occur. At least not to any great extent. Most of the reactants remain unchanged, and there are few products produced. In other words, this would be a situation where we have no reaction. So go to completion, all reactants are transformed into products, no reaction. None of the reactants are transformed into products. And then we got some exercises, which I will let you do on your own time, because we are going to go and talk about entropy and enthalpy. You sound so excited. And actually, this should look very, very familiar to you because you saw this in the summertime. Yes? Yes, you did. I think I left it basically unchanged. This is page 110. Enthalpy. You should be not so bad with enthalpy. We've been dealing with it for quite some time now. Okay. Enthalpy, the official definition for Chem 12 is the heat content of the system. So if you're asked for a definition, that's what you would say. There is the big black book. There it is. Remember, if we look up the real definition for enthalpy in the big black book, enthalpy, a quantity defined by the relationship H equals E plus PV. The enthalpy change, delta H for a reaction, occurs at constant pressure. That occurs at constant pressure is the heat evolved or absorbed by the reaction. Delta H is equal to Q little p. Anyone want to learn that definition? No. All right. So for Chem 12, you're going to call it the heat content of the system. AP is not going to ask you to define it. I'm going to tell you to think of it, as I have in the past, as the potential energy contained in the chemical bonds and atoms. Because atoms contain potential energy too. Okay. Does nature love to be at high potential energy or low potential energy? Nature loves to be at low potential energy. So a ball rolls naturally or spontaneously down the hill. To make a ball roll up the hill, what if I wanted the ball to roll up the hill? I would need to do some work. If I do some work, that is a non-spontaneous process. Okay? So nature likes to be at low enthalpy, low potential energy. So nature likes exothermic reactions. Would you ever say that for me on a quiz or a test, that nature likes something? No. I would say that the exothermic direction is thermodynamically favored. Thermodynamically favored or thermodynamically unfavored is the language that AP prefers. Since it's associated with a negative change in enthalpy. Since it involves a decrease in enthalpy. And if you think of enthalpy as potential energy, that makes sense, right? What does nature like? It likes a decrease in potential energy. It likes to roll, the ball likes to roll down the hill, okay? This right here is AP language. Based on enthalpy for an exothermic reactants, are products favored or are reactants favored? Products. Okay? Which begs the question, then why, oh why, would an endothermic reaction ever occur? Nature's like, oh, exothermic, best. So good. But there are endothermic reactions that happen all the time. In an exothermic reaction, products are favored because they are at the lowest potential energy. In other words, they are at the minimum enthalpy. Nature always favors the side with minimum enthalpy. Which side of the reaction is favored in an endothermic reaction? The reactants. Hello, eraser. Why are you not erasing? Ah, yeah. That's okay. The reactants are, what is that language that we want to use? Thermodynamically by minimum enthalpy. Since the reactants have the lowest potential energy, the minimum enthalpy, then minimum enthalpy favors the reactants. When we say an endothermic reaction, we mean the forward reaction is endothermic. If we don't specify, you're always going to be referring to the forward reaction. If we say an exothermic reaction, we mean the forward reaction is exothermic. If it was specified, then you just go with what is specified. All right, please tell me, because I know you don't remember this from this summer, which side, products or reactants, does minimum enthalpy favor for each of the following? Okay, A, products or reactants? Reactants. B, where does that 30 kilojoules go? On the left or the right? So, which side is favored by minimum enthalpy? Products. C, products. Where does the 10 kilojoules go for D? On the left. So which side is favored by minimum enthalpy? The reactants. Okay, excellent. Minimum enthalpy always favors the side with the heat term because that is the exothermic direction, okay? So it always favors the side with the heat term and the exothermic direction. So there was a little confusion when a few people were writing their quiz about whether you were referring to a direction or a side of the reaction. So if you're talking about the reactants, you're talking about a side of the reaction. If you're talking about what happens as A goes to B, that is called the forward direction. If you're talking about when B goes to A, that is the reverse direction. So you have to really think about the terminology you're using and making sure that you're specifically using the correct terms. Now, entropy, and we will dig deeper into this next day because we'll get into sort of more of the AP definition of it. But entropy is the randomness or disorder of the system. I've not been too bad this year, but what happens to my desk if just left to its own natural state? It decomposes, basically, yes. I mean, I've only been here for like half an hour when I'm not teaching, and already, boom, there's like stuff everywhere, yes? In order for there not to be stuff everywhere by the end of the day, I would need to put in some work. Yes, naturally, I don't need to do anything and it becomes a great big mess, okay? So nature tends towards more randomness or disorder. This is not an excellent definition of entropy. This is a Chem 12 definition. We'll get into a bit more of an AP definition later. The symbol for entropy is S, I guess because they ran out of things with E. And the change in enthalpy obviously is delta S. And as we were saying, nature tends towards more randomness. In other words, maximum entropy. So unlike enthalpy, where it wanted enthalpy to be small, the potential energy to be small, we want maximum randomness. Maximum entropy. So movement towards maximum entropy is spontaneous. The AP way of saying spontaneous Any guesses? Thermodynamically favored. However, I feel like as you go off to university, you will still hear the word spontaneous and non-spontaneous, as you will within my worksheets and within Hebden, because those are more geared towards Chem 12. So this is the Chem 12 language. And this is the AP language. Now, if you're moving towards minimum entropy, is that spontaneous or non-spontaneous? That is non-spontaneous. How could you say that? It is thermodynamically not favored or unfavored, okay? They couldn't have chosen like bigger words, could they? You know how much I love big words. I've almost considered going to the American spelling of favored just to get rid of one of the letters. Okay, so we have our spontaneous process goes from tidy bedroom to messy bedroom. This would be, I'm just going to say thermodynamically favored. And this is thermodynamically unfavored. So we could go from a more ordered system where we have a solid, for example, and it ends up as a gas. The forward direction is spontaneous or thermodynamically favored. And the reverse process is non-spontaneous, thermodynamically unfavored. Is this ringing bells from the summertime? A few of you, okay. So now, easiest way to look at things, we're going to start with our gas, solid, liquid gases, our states. So we're looking at the entropy of different states of matter. And does it make sense to you that a gas is the most random? Yeah? Okay. And aqueous is less random because if it's aqueous, it is in a, like, if I had a liquid in this container, it can't like zoom off to the other side of the room, right? It's stuck in whatever liquid it has. Liquids are pure substances, so they are less random than mixtures. And solids are very ordered and there is little movement, so they are the least. So if you have states of matter, go with that, okay? If you don't have different states of matter, then if all the particles are in the same state, like let's say we had all gases, then the side with more molecules is favored by maximum entropy. More things make a bigger mess than fewer things, hence minimalism. And what's her name? Maria Kondo, whatever her name is. I don't know. You guys don't know what I'm talking about. That's all right. Gases are vastly more random than any other state. If you can maximize gas molecules, you maximize the entropy. You can ignore the number of particles in other states. In other words, when looking for maximum entropy, the number of gas molecules is the most important. Which side does maximum entropy favor? And what is the sign of delta S for the forward reaction? Do you guys want to do those ones? In A, maximum entropy favors the products because we've got 3 gas molecules, and over here we have only 2 gas molecules. So that favors the products. And so delta S, is it positive or negative? Positive, yes. Okay. In our second one, we have aqueous and aqueous, and then on the right-hand side, we have solid. So maximum entropy favors the reactants. Solid is the least entropic, I guess you could say. And so in this case, delta S is negative. Okay, now we have a solid and a solid and a gas. And the fact that you have a gas over here overrides everything else, which means that maximum entropy favors the products, and delta S is positive. And in our last one, let's see, we have, this is 7.5 gas molecules. And over here we have 6 gas molecules. So 7.5 beats 6. All right, so maximum entropy favors the reactants, and delta S is negative. And our last one, we go from a liquid to a gas. So maximum entropy favors products, and delta S is positive. Is that all good? Cool. All right. Now, if you have both big randomness and minimum enthalpy, that would be your low potential energy. if both of those are in the products, that means maximum entropy is pushing towards products. And minimum enthalpy is pushing towards products. And if you've got two things pushing towards products and nothing pushing back, what's that reaction going to do? It's going to everything's pushing towards products. It's going to go to completion, okay? It's going to go to completion. And the KEQ will be very large. If you have both maximum entropy and minimum enthalpy favoring the reactants, in other words, they are both pushing towards the reactants, if everything is pushing that way, are your reactants going to react? No. This reaction will not proceed. So when we're writing our arrows, going to completion is a forward arrow. Okay? If it does not proceed, we put an X through our arrow, and KEQ will be very small.
Wait, so if it's not proceed, it will not proceed, go backwards.
It could go backwards if you were to put products in.
So like for a second.
If you had products, it would proceed in the reverse direction, spontaneously. Yeah. Now, just so we're clear, it is possible to have a spontaneous reaction that does not go simply because the activation energy is too high. Okay? It wants to get there. It's like, I really want to get there. But like if it's too cold, the reaction will not proceed because the activation energy is too high. That's a separate issue altogether, and we'll talk a little bit more about that later. Okay? When maximum entropy and minimum enthalpy favor opposite sides. So in other words, either one is pushing forwards and this one's pushing backwards, or we have this one pushing backwards and this one pushing forwards. Guess what kind of situation we will end up with? We will end up with an equilibrium. It is still a spontaneous process. It will spontaneously reach an equilibrium. It goes back and forth, and of course we've got our equilibrium arrows, and KEQ is not very large, it's not very small, it is close to 1. Now close to 1 just means it has a value that's not like infinity, okay? You can have KEQs that are times 10 to the negative 41, and that's still close to 1. Okay? It just means that it doesn't sit completely one way or the other. Okay? Close to 1 could mean a KEQ of 10 to the negative 12 because 10 to the negative 12 is close to 1. When compared to really small KEQ values like 10 to the negative 57. But you do not need to be able to decide what close to 1 means. You don't need to decide that. It just means not very large or very small. Whatever those mean, you don't need to worry about it. Okay? Yeah. So, if KEQ is greater than 1, whoa, what happened here? I don't love this bit because I feel like if KEQ is greater than 1, how much? At any rate, let's get rid of this. If we have a large KEQ, it goes to completion. If we have a small KEQ, it does not go. Very large, very small. There, that makes me happier. If KEQ is approximately equal to 1, it forms an equilibrium. In this reaction, which side has higher entropy and which side has lower entropy? Is that what you guys got? Okay, excellent. So what that means, which direction is entropy pushing us? Entropy is pushing us to the right. All right. Enthalpy, which side is higher and which side is lower? Why? Does that make sense? We've taken 10 kilojoules of potential energy in the reverse reaction, and we've turned it into 10 kilojoules of potential energy. So the left-hand side has more potential energy in the chemicals. And so the enthalpy is higher on the left and lower on the right. Which way is enthalpy pushing? Towards the products. So what kind of arrow should we have? We should have a one-way arrow. Is this reaction spontaneous or non-spontaneous? Spontaneous. I'm just going to say spawn. Does this reaction go to completion, not proceed, or form an equilibrium? Goes to completion. And we've already put the correct arrow in the box. What is the value of KEQ like? Is KEQ very large, very small, or approximately equal to 1? Very large. I think we can get through one more example before we leave today. Yes? If you have trouble figuring out the enthalpy, draw your little diagram. Be like, okay, I've got, why will you not draw? Okay, that's an endothermic reaction, right? So enthalpy is low for the reactants and high for the products. Spontaneous or non-spontaneous? Non. Non-spawn. Does it go to completion, form an equilibrium, or not proceed? Not proceed. What's KEQ like? Very small. And you can guess what the third one's going to be, right? It's going to be an equilibrium, okay? I will put your homework up on Teams. It's going to be 2.3 E.
We're actually completely like anybody from our football. Not for 2 She got not so bad. Oh, today. Post the link. Bro, there's like 8
We talked